Hello, I am Keigo Imai. This talk is about multi-party session programming with global protocol combinators, which is a joint work with Rumiana Neikova, Nobuko Yoshida, and Shoji Yuen. In this presentation, we will put emphasis on the construction and typing of global combinators. We introduced OCaml MPST, a library for concurrent and distributed programming. This is strongly inspired by and based on multi-party session types. In this framework, if a program is well typed by OCaml type checker, then the program is free from deadlocks. Here is an example programming in OCaml MPST where we write the three-party link protocol. At first, the programmer specifies a communication protocol using global combinators. This protocol can be read from left to right, saying that the message labels ping, pong, and pang are circulated from A to B to C, then back to A. This simple protocol is actually valid, also called waveform in literature. The protocol description allocates a tuple of session channels, here CHA and CHB and CHC, connected with each other, which is shared by OCaml threads. The thread A communicates on CHA, thread B on CHB, and thread C on CHC. This channel has session types enforcing the protocol in a statically typed way. As protocol is deadlock-free and protocol is enforced to the program, we can conclude the program is deadlock-free. This is actually surprising, as it only uses OCaml type checker. The notable feature of global combinators is projection. The endpoint projection in the session type theory derives the session types, which explains the behavior of each participant from the local viewpoint. Throughout this presentation, we use graphical notation of session types based on communicating automata. Type of CHA, here B bang ping is an output of ping to B, and C question mark pang is an input of pang from C, showing the behavior from the viewpoint of thread A. Similarly, the session types for CHB and CHC reflect the local behavior of the link protocol. And here is how global combinators are modeled in OCaml. Finished combinator is the basis for this. It is the protocol with all three participants in the final state, and no further communication will take place. The arrow combinator updates the sessions. For example, assume C to A pang is applied to finish as in the end of the link protocol. This arrow combinator C to A is a curried function, taking label pang and the tuple of channels, following the convention of the lambda calculus. This function prepends the communication action on each channel C and A. For A, it adds reception from C, and for C, it adds transmission to A. In this way, global combinators applies to the tuple of session channels, building larger session from the smaller parts. In this bottom-up manner, the arrow combinator will build the tuple of session channels conforming to the protocol. The terminate session channels are then updated to C to A communication channel, then preceded by B to C communication, which is further preceded by A to B communication. Then, how do we implement such session typing scheme in OCaml, and what about more complex protocols like recursion and branching? For this, we adopt channel vector encoding of session types, which represent session type structure using record types and variant types. Output session type is encoded as a nested record type. Here Z is angle bracketed type. The outermost B is the destination of the sending, and ping field in the inner record corresponds to the output label. The bang V symbol here is the channel for transmitting the payload of type V, and the next denotes the next state of the session. On the other hand, input type is encoded as a variant type, here square bracketed type. Note that the wrapping record field C is the source of the input action, and its constructor pang stands for input labels. And the question mark before the bracket denotes an input channel, and V is payload. Now let's see how session types are enforced to communication programs. For this, let us consider the thread B of the link protocol, extended with stop action, in which the stop is forwarded to C. B first receives from A, making an external choice between ping and stop. The channel vector type looks like this. External choice between possible labels are ping or stop. For ping, we also assume payload type is string, and for stop, the payload is unit. Here is the implementation of thread B. The external choice is implemented using pattern matching against the result of the reception from A. In the patterns, the continuation is bound to variable CHB. shadowing the previous occurrence of CHP to ensure not to repeat the same communication action. In both cases, the next channel CHP is used to send the label to C. For ping case, the label Pong is sent with the payload text, and in the stop case, the label stop is just forwarded to C with the unit payload. In both cases, the session is eventually closed. Note that linear use of channel CHP is mandatory here. We provide two flavors of linearity checking, one for static linearity checking and the other one for dynamic checking. Let's go back to the protocol side and see that we can model more complex protocols including branching and recursion. For recursion, here is the recursive link protocol using the fixed combinator, where the variable self is bound to the beginning of the loop, just repeatedly circulates ping, pong, and pang. And here is the session types for recursive link protocol. Thanks to the equally recursive nature of the OCaml type system, the session types for such a recursive multi-party sessions are directly represented by OCaml types. Here is the channel vector types for each participant. The mu operator binds the variable t to itself, making a recursively nested record type, which represents recursive session types. This is a recursive protocol with additional stop branch. The @mark operator is a function application which is right associative, just eliminates several parentheses. I use message sequence such as on the right. Here, the first branch is the usual ring protocol, and the other branch stops the ring. And we remove recursion for the presentation purpose. Even in this simpler setting, branching can be a major source of errors in the protocol. Assume the programmer made a mistake in the protocol. The programmer made a mistake at the end of the second branch by writing C to B, which is opposite. Such a protocol is said not well formed or just meaningless. To see this, consider when C should send stop to B. According to the protocol, the system enters to the second branch when A sends stop to B. However, in this situation, C is never notified of the decision made by A. Consequently, it is not possible for C to decide to output the stop message. The design of channel vector types plays a central role for detecting such errors. At first, consider how a valid branching structure is typed using global combinators. Let's focus on C. In the branching, we have two alternatives, the former one for receiving pong and the latter one for receiving stop. According to session type theory, this sort of branching is valid, and they are merged into an external choice waiting for either pong or stop. Our key finding is that such a session merging is simulated in the global combinators by utilizing subtype relation on records and variants. In this case, pong can be subsumed by pong or stop, and stop can be subsumed by pong or stop as well. Accordingly, the OCaml type system will compute the merged session type to receive either pong or stop at the participant C. In this way, session merging coincides with the least upper bound of two session types if it exists. Now let's see how the meaningless protocol we have seen is rejected by the type checker. Recall that the programmer made an output at C in the second branch, sending stop. As we have seen, branching between such two kinds of behavior are not justified. As there is no common supertype between variant types and record types in OCaml type system, we cannot give any type to this branching, and correspondingly, OCaml type checker will reject it as a type error. In summary, by choosing appropriate encoding of session types using records and variant types, we faithfully model the session type merging in channel vector types. Now let me wrap up our presentation. Firstly, we gave the semantics of the global combinators in the way that each local behavior is built from the bottom up. Secondly, we designed channel vectors using standard record and variant types, offering programmers to write multi-party sessions in an idiomatic manner. Thirdly, the design of channel vector types allowed us to validate protocols using standard type system via subtyping, thus obtaining a protocol validation framework in a general-purpose programming language OCaml. A future work would be to explore design space for session type programming in a real-world OCaml programming, for example, Mirage OS operating system written in OCaml, or utilizing translators from OCaml to JavaScript for the web application development. Thank you for your attention.